We humans have always looked up at the stars and asked the biggest questions imaginable. Where did all this come from? And maybe more importantly, where's it all going? For decades, science seemed to have a pretty clear answer for the end of everything. But now, well, that answer is starting to look a little shaky. So let's get right to it. How will the universe end? Is it going to be a slow, cold, lonely fade to black, or a fiery, dramatic collapse back into itself? It really all comes down to this epic cosmic tug of war between gravity, which is always trying to pull things together, and some kind of mysterious force that seems to be pushing everything apart. For the last, 25 years or so, the scientific consensus has been pretty darn firm. The story went like this. The universe is expanding, and it's just going to keep expanding forever, growing colder and emptier as it goes. This wasn't just some fringe idea either. This was the conclusion that won a Nobel Prize and became the absolute bedrock of modern cosmology. So in one corner, you've got the reigning champion, what we call the Big Chill or the Big Rip. In that scenario, the universe just expands forever until all the galaxies are these lonely islands and a vast, cold, dark nothingness. And in the other corner, you have the old contender, the Big Crunch. That's the idea that gravity eventually wins the tug of war, reverses the expansion, and pulls everything, and I mean everything, back into a single, unbelievably hot and dense point. For a long, long time, the Big Crunch was pretty much counted out. Yeah, the knockout punch for the Big Crunch theory seemed to come in the late 1990s. Astronomers were looking at these distant exploding stars. They're called supernova, and they found something just astonishing. It wasn't just that the universe was expanding, the expansion was actually speeding up. This discovery was so revolutionary, it completely flipped our understanding of the cosmos on its head. So what's hitting the cosmic gas pedal? Well, we gave it a name: dark energy. And the scale of this stuff is just staggering. See, normal matter, that's you, me, the planets, the stars, everything we can actually see and touch, that only makes up about 5% of the universe. The rest, the vast majority, is this invisible, totally unknown dark energy that's constantly pushing space itself apart. Okay, but here's the thing. The entire theory of this endlessly accelerating universe rests on one absolutely critical assumption: that dark energy is a constant, unchanging force. But what if it's not? What if this dominant force in the entire universe can actually change, or evolve, or maybe even get weaker over time? And this brings us to some pretty big cracks that have started to appear in our perfect picture of the universe. For years, there have been these little nagging observations that just don't quite fit the standard model, suggesting that maybe, just maybe, our picture is incomplete. The most significant of all these puzzles is something known as the Hubble tension. Honestly, it's become one of the biggest controversies in modern astronomy, and it's a fundamental disagreement in how we measure our own universe. Here's the problem in a nutshell. When we look deep into the past at the early universe, using the leftover heat from the Big Bang itself, we can predict how fast the universe should be expanding today. But when we measure the expansion directly using stars and galaxies that are much closer to us, we get a different number, a faster one. Both of these measurements are super precise, but they just don't agree. And that's a huge clue that we're missing something in our cosmic rulebook. And that, right there, brings us to the plot twist. Because recently, these massive new sky surveys have started delivering data that doesn't just poke at the edges of our model. It challenges the very nature of dark energy itself. Okay, so you have these incredible projects like the Dark Energy Survey and the Dark Energy Spectroscopic Instrument. I mean, these things have created the largest 3D maps of the universe we've ever had. And their first results are provocative. The data is hinting that dark energy isn't some constant force at all, but that it's actually changing and maybe even weakening as the universe gets older. This quote just nails it. It perfectly illustrates the new challenge. Remember those supernovae I mentioned, the ones that were the main evidence for acceleration? Well, it turns out we made a key assumption, that they were all perfect standard candles, meaning they all had the exact same brightness. But this new research suggests that's just not true. It seems that stars back in the early universe were a bit different, and they might have produced supernovae that were, on average, a little bit fainter. So you see where this is going, right? This is the key takeaway. If those early supernovae were naturally fainter than we thought, it means we've been misjudging how far away they are. They're actually closer to us. And if they're closer, it means the universe hasn't been expanding as fast as we believed all this time. Suddenly, the evidence for acceleration just evaporates, and the data now seems to point to a slowdown. And if the universe's expansion is slowing down, well, that puts the Big Crunch, that old, once discarded theory, right back on the table.
But this isn't about just dusting off an old idea. It's being supercharged with brand new physics and, for the first time, some actual data to back it up.
The entire fate of the universe really hangs on a single number. It's a variable called omega, the density parameter. And it's a pretty simple ratio. It's how much stuff is actually in the universe, compared to the exact amount of stuff needed to just barely stop its expansion.
So you really have three possible fates. If omega is less than 1, the universe is open, not enough gravity, and it expands forever. If it's exactly 1, it's flat, and it just kind of coasts to a stop over an infinite amount of time. But if omega is greater than 1, there's enough stuff and gravity wins. The universe is closed, and it is destined for a big crunch. And for the first time in a long time, new models are suggesting that this last option is a very real possibility.
So how on earth could this work? Well, one of the leading new models suggests that what we call dark energy is actually two different forces in disguise. One is a dynamic field that pushes things apart, and the other is a constant force that actually pulls things together. Early on, the pushing force was stronger, and that's what caused the expansion we see. But over billions of years, it's been getting weaker, and eventually that pulling force is going to take over and trigger a total collapse.
Now, okay, before we all start setting our cosmic clocks for doomsday, we've got to inject a very healthy dose of scientific reality here. As one of the astronomers working on this new data pointed out, these findings are just a hint. They are incredibly exciting, for sure, but they are not yet statistically significant enough for us to call them proof. This scientific debate is very, very much alive.
But let's just have some fun. Let's follow this tantalizing hint to its logical conclusion, because if this new model turns out to be correct, it doesn't just change our distant future. It gives us a specific, testable timeline for the end of everything. So according to these new calculations, the universe is about 13.8 billion years old today. In this scenario, in roughly 7 billion years, its expansion would grind to a halt at its maximum possible size. And from that point on, it would begin to contract, all culminating in a big crunch approximately 20 billion years from now. It basically gives our entire cosmos a finite lifespan.
And the end? Well, it would be spectacular. As the universe contracts, galaxies would start rushing together and merging into one another. The background radiation of space would get hotter and hotter, eventually cooking stars from the outside in until they literally evaporate. And then in the final moments, the temperature would become so extreme that atoms themselves would be ripped apart, just before everything is crushed back into that singularity, an infinitely hot, infinitely dense point.
Which of course leaves us with one last, truly mind-bending question. If the universe can collapse into a singularity, could that event trigger another Big Bang? This idea is known as the Big Bounce, and it suggests a cyclic universe, one that is born, dies, and is reborn again and again, maybe forever. Is our entire existence just one chapter in an eternal cosmic story? Right now, we just don't know. But for the first time in a generation, that question is officially back on the table.